Hi everyone, my name is Maggie and I'll be your host for today's webinar on test, training, and exercises for space professionals. Today's webinar will be delivered by Jim Fields. Jim joined AGI in 1996 and is currently the Chief Engineer for SEG, the Space Event Generator. We also have Ben on the line, an aerospace software engineer who's been with AGI for 2 years.
Hello. Yes, my name is Jim Fields, and as Maggie said, I've been with AGI for nearly 23 years. I've worked on a number of different products while I've been here, SDK and ODTK. I moved into the SSA realm, and then lately I've been focused in the TTX area, working on a product called SEG. And so today we're going to be talking about TTX, which is test, training, exercises for space professionals. And we're going to take a look at SEG, our space event generator, and see how it can be used to support TTX. And if we have time, we're also going to look at some example scenarios. I'd like to show some cases where we're creating test or exercise data using time-shifted data that was created in some other time frame, and we're moving that ephemeris to compare against a current space object catalog and showing prox-ops from one of these objects going around another satellite. And we'll look at that interaction between SEG results and our other products, SDK and ODTK. And I'd like to show an example where we're looking at covariance results from coming from processing data that SEG is producing. So why should we care about space threats? This is the crux of the TTX. We all know that modern threats exist, whether they're obvious kinetic threats like direct descent, anti-satellite weapons, or more subtle tactics such as close proximity operations for intelligence or interference missions. And whether it is a compromise in secure communications, or loss of service, or even the loss of a platform, the security of modern cultures depends on space-based assets. And any of these losses would have a serious impact. So we have to understand these threats. Satellite operators have to be ready to detect and respond to potential threats in ways that have been practiced, while at the same time account for their own capabilities and limitations. And that takes a lot of training. And we have to train better. The US outspends China 4-to-1 in space, and yet China is closing the performance gap. Clearly, our current tools and our approach to space training is insufficient. We need to find better ways to address these threats. In the age of Google and Amazon Prime, relying on 20-year-old software and multi-month training cycles in defense of critical assets is just unsatisfactory. A military cornerstone is train like you fight and fight like you train. And here at AGI, our former naval flight officers can attest that that is the way it's done in the air community. And they had the tools that they needed to do this. They trained in simulators that were functionally identical to the aircraft that they fought in. And this is where we need to get to in space. Based on our conversations across the market and with our customers, and based on the exercises we have supported, like Global Sentinel, we have identified two main challenges. First, our Air Force group commanders know that their training tools aren't perfect, and they're doing the best they can with the tools available. But it takes weeks to months of work to generate the data they need to run an exercise. And this extra time costs more and leads to lower readiness levels. If you're only training monthly instead of weekly, you can't stay current. It also means that you can't keep up with evolving threats. And slow tempos are not viable if you're trying to rapidly execute potential what-if scenarios, which is critical to tactics development. So frequent training is critical, but inhibited by and made costly with today's tools. The second significant challenge is accuracy. Any pilot walking into a simulator expects it to behave like the real aircraft, yet today's space data simulators use simplistic representations of the real thing. They often model only a portion of the catalog. Typical exercises include less than 100 objects. And that orbital data then gets passed around based on assumptions of persistent sensors and perfect orbit determination. Whereas in reality, operators have to deal with up to 20,000 background objects. Sensor data is noisy and sporadic, and the quality of OD solutions depends on the quality of the sensor data. And this kind of unrealistic training without real-world fidelity leads to poor preparedness. Just a sec. It was with these challenges in mind that we laid out a set of requirements for an ideal test training and exercise support tool. Any viable product would have to have sufficient scope and had to handle a majority of the regular threats and space events experienced today. It had to be realistic, employing full fidelity modeling. And it had to be quick and timely. Again, you can't model what-if scenarios and expect to make progress if you are waiting days or weeks between runs. We wanted to create a scenario, run it, learn from it, change it, and run it again within minutes. To accomplish this, it has to be highly automated. And of course, another issue is security. In the places where we work, security is a key concern. And finally, interoperability. Many of our customers have their own formats and their own tools as well. We envision ultimately an ecosystem of tools, each with different strengths. For example, one tool may excel at comms modeling, while another might allow detailed modeling of a low thrust trajectory. We wanted a tool to bring them all together into a coherent scenario, one that was built flexible enough to interact with the format of any of our customers. And now that we had a list of product requirements, we took the next step. We built a product named SEG, which is our space event generator. SEG has the following capabilities. It allows us to create multiple types of space events in all orbit regimes. It's able to create individual or linked sets of events, where linked events are where one space object is involved in a series of sequential events. For example, a space object can be launched, do maneuvers, enter into proximity operations around another satellite, then maneuver to go conjunct with another satellite. And SEG can solve for the intermediate maneuvers required to link these events together. Events are combined into scenarios, or another way of saying this is a scenario is a container for a set of events over a common time span. SEG outputs observations, ephemeris, and sensor in-views. And these OBS can then be fed into a flight dynamics or catalog processing system. Ephemeris can be viewed directly or may be downloaded for use in SDK. And SEG supports planning, training, testing, and exercises. And it also includes a user-friendly user interface as well as web services for integration. And later on, hopefully we'll have time to look through that user interface. So SEG meets the requirement for scope by offering 12 different space event types. We have reentry, proximity operations, deorbit, rendezvous, breakup, conjunction, deployment, maneuvers, orbital intercept, launch, and the next set of events coming up in our next release will be ASAT, direct descent, anti-satellite, and docking and separation. Again, SEG has user-friendly event workflows, and the gist is really that it allows an operator and not an astrodynamics expert to be able to create these accurate events and get results out. Some of the use cases that SEG supports are repeatable, tailorable operator procedure training. So if a conjunction is predicted, how do I respond? What steps do I take? Day in the life operations training can be, I follow a checklist of daily activities. I'm going to generate data, need to process it, get solutions, and feed them through a system. And SEG can be used to generate the data to provide that. Systems performance tests. I think I jumped a page there. For example, I could load observations in batches to test the orbit determination process, compared OD-generated ephemeris predictions against the simulated truth ephemeris that SEG is providing. Proof of concept studies, for example, adding sensors. If I add more sensors, what does that do to my ephemeris estimates? I can do simulated over live, where I'm adding simulated events to a historical catalog, or even adding new tracking data for an old event over historical observations. And we have exercise support, mission planning, and what-if tactics development. For example, when can I perform a maneuver that won't be detected by an optical sensor network? So our TTX workflow, so we start off by cloning an operational SSA database. And an SSA database is going to contain a set of catalog object states and a tracker system. So this is really geared towards someone who's maintaining a catalog of objects in space, where you have either a full SSN catalog of 15,000 objects, Or you might have your own set of objects that you're concerned about, that you're tracking or you're generating ephemeris for. But the main point of this is that SEG is using this database as its source of information for building scenarios and processing data. Once we have an SSA, once we have a database cloned, that through the user interface, the user builds a scenario, adds events to that scenario, and each event has a sensor cadence, and the sensor cadence, which we'll get into detail later, is used to define how much tracking data is going to be generated for each object involved per event. And the user can define a set of background catalogs, which can be used to just populate their scenario with objects to create as much noise or as much complexity in their scenario as they want. The next step is to run the scenario and generate observations and generate ephemeris for all of the objects within that scenario. And then once that data is stored, that data goes back onto this database, and that information can then be downloaded and shared with other tools. So this next graphic shows that data flow. This kind of golden orange color is the input data, where we have our sensor models. So we have sensor locations, measurement types, and biases. Those are coming from, typically defined by like an SSN network. And there's initialization data shown here at the bottom, where we have space object states and ephemeris that are coming from that catalog. And those are going to define what the initial states are for as many objects in space that we're concerned about. The user-defined event data is going to be input through our user interface or through the web services. And so that's something to note here, that we have a database that houses all of the data that's used in these scenarios. And between the user interface and that database are a set of services that are used to get data to and from the database. And these services retrieve and store data as well as kick off the data generation. And so the results, the observations, and the ephemeris are stored back in this database as well. So this is our landing page for our scenario, for our user interface. And this shows basically there are many scenarios here, as you can see. Each scenario has a name and a description, and each scenario has a time span. You'll see an analysis start and then an analysis stop. And many of these are around the same time span since they are using data from the database snap, which is providing space object catalog states at a particular time. On the right side, you will see the scenario details for the highlighted scenario up here. And there are buttons here to allow us to open up the scenario and view the events of the scenario, or go directly to the results or to generate output for this particular scenario. So we're going to return to this scenario shortly. So here's a sample event workflow where we're adding a conjunction event to a scenario. And this top of the screen is pretty much identical to all of the events in the scenario. We provide an event name, a description, some other data, and we're not going to get into that now. And one selects the event type. In this case, it's conjunction. And this second block of data is the conjunction data, which is based on this event type. And this chunk of data will change based on what type of event it is. So for a conjunction event, ultimately what we have is one object passing very closely to another object. And so the data that we have here, well, first of all, we select a primary object, the object being approached, or the target, as you will. And we define the time of closest approach for this conjunction. And then we have other data here that defines what the relative position should be between these two objects at that time of closest approach. There are a lot of inputs here, and we actually have tooltips and documentation for each of these inputs to describe exactly what they are. And down here at the bottom, we're defining the secondary object. This is the object that's going to be doing the conjunction, or the secondary, or the actor object. And we can either, there's one of two choices. There's this is a new simulated object, which means we're going to create an object that doesn't currently exist in the catalog. However, we could also take an existing catalog object and convert that into an actor so that it will be maneuvered so that it will wind up doing a conjunction with another object that's also in the catalog. And at the bottom of the page, which isn't quite shown here, one defines a sensor cadence, which is going to be used, again, to define how many observations are going to be generated for each of these objects over this event time span. And we will get to that again later on. But not then. All right. So our next slide is discussing what a catalog event is. A catalog event is a single event that groups together a set of objects which are propagated over the scenario duration. And these objects are going to share a common sensor cadence, which again defines how many observations are going to be generated per object over the duration of the scenario. We allow multiple catalog events in each scenario in order to support any grouping strategy that you might want. For example, you might want a catalog event that just has a certain number of geo-catalog objects that are tracked infrequently, or you might have another set of geo objects which are tracked very frequently. So you would want those in two different catalog events and define two different sensor cadences so that they can have the correct number of obs per object generated. You can also group these just by, I could have all my LEO satellites that are in the European Union in one catalog event, just to kind of partition things as you see fit. And there is no limit on the number of objects per catalog. Ultimately, this allows a fully realistic background catalog, and it allows a trainer or exercise conductor to adjust the difficulty of the scenario. Because if you're processing obs especially, the more obs you have coming into your system, the more you have to deal with obs association and orbit determination, trying to sort out which observations belong to which satellites. So our next slide, sensor cadence, we've mentioned it a few times. Each space event, ephemeris event, or catalog event can specify its own sensor cadence. And the sensor cadence defines how many observations are created per object per event. So what we do is, given the locations of the sensors and the constraints that the user can define via services on each sensor, we compute all available access intervals between each sensor and each space object. And from those, SEG will subselect a set of intervals to meet the cadence definitions and generate observations over those intervals. If you're familiar with the SSN tracking system, sensor cadences in SEG can be configured to match tasking codes in SSN. For instance, you could request that a geosatellite be tracked using one radar track every 2 days, 2 ground-based optical tracks per day, and 3 space-based optical tracks per day. So if it's possible to achieve it, SEG will provide a set of data as you have required, or as you have requested. And the ability to define individual cadences creates a more realistic training scenario versus assuming persistent sensor coverage, and allows the trainer direct control over the difficulty of the scenario. Plus, the ability to define the sensor model measurement models, the noise and the biases, allows us to model the realistic uncertainties that we talked about in the requirements. So if you're doing orbit determination especially, and you want to realistically model what those sensors can generate as far as measurements, SEG allows you to do that. So the architecture, we mentioned earlier that SEG uses services to communicate with an Oracle backend database. And the generation of scenario data is automatically distributed using SDK scalability. That kind of goes along in the background, and that's all run by services. We have a fully documented application programming interface, or API, which we'll see shortly. And we have support for both REST and SOAP services, and is completely automatable. We use a similar hierarchy to Systems Toolkit for scenarios, where SEG has a scenario which governs the simulation environment, and entities with events produce ephemeris based on the inputs, and is interoperable with SDK using visual data files, or VDF. And data produced from SEG can then be fed into your exercise engine of choice. So I imagine we might have some questions at this point. How are we doing?
We actually have a couple of questions.
Okay.
Are there modules or files that I need to download?
SEG is its own product. I believe that the SEG installation is going to have most of the files that you will need, at least to get you started. Some of the things, as any, if you're doing anything near real time, of course, you'd probably be wanting to download EOP and space weather as it's relevant to your time frame that you're working in.
Great. Another question is there a beta that SDK users can access to play around with?
I don't know about a beta version. We do have released versions. There's a 2.15 that has been released of SEG. I think I would direct them to a salesperson or one of our engineers to help them out.
Will do. And then how do you search the tracking ID?
How do I
search the tracking ID?
Search it?
UI.
Through the UI?
Mm-hmm.
Oh, yes. Oh, right. Exactly. Yeah, there. We might have a chance to actually demonstrate that. There is a grid that comes up, or there's a panel that comes up, and you can search all of your objects in your space catalog and find the, by tracking ID, which object you want to include in a scenario. If I'm understanding that question correctly.
I believe so. And then we'll save the rest for your Q&A section.
Okay.
We're now going to show a couple of demos related to TTX test training and exercises. The goal is to show some examples of how SEG is used and the data that it creates, but this isn't going to be a full walkthrough of all of the features of our product. This will be more directed to a few areas of interest. We'll start on the landing page of SEG, which is our space event generator. As a refresher, SEG is a standalone product built using a service-oriented architecture, meaning that we have a web-based user interface that uses services to access an underlying database. The database contains many pieces of data used by SEG, including a set of space object states, which represent the catalog of objects in space at some time. Those states were created based on having processed observations up to a certain date, meaning they're all valid at a particular time. The reason this is important is that when SEG is going to use these states in a scenario, it's going to propagate that state from its epoch through the time span of the scenario. So therefore, we want our scenario time spans to be reasonably close to the state epochs in our database. Since the states in the database we're seeing here were tagged at or before April timeframe, we see that many of these scenarios begin around that time. So we're going to look at an example of using an ephemeris event in SEG to pull in an externally generated data. As we talked about in our presentation, an ephemeris event allows us to use an external tool to create as complicated an ephemeris as we want, or allow us to use ephemeris from a real mission. In either case, we can move that ephemeris to any time of interest. For this example, we have a launch profile developed by an engineer, and we want to use SEG to generate data, observations, and ephemeris for use in testing some external tools and see how that launch ephemeris compares to our current catalog. So we're going to start by creating a scenario. Actually, we're going to start by looking at the data that we have from our engineer. So we have a folder with ephemeris files in it. There's a communication satellite, a payload, a second and third stage. We're going to import these into SEG, and we're going to use these, we're going to use ephemeris events, rather, within a scenario to create these events. So we have a 2019 launch ephemeris that spans a number of days, If I open that up, what I'm going to see is there is a series of events already in the scenario that I've already added. So we have the communication satellite here, the payload object, the second stage, and these are all ephemeris events. And to show you how that is added, we're going to add a new event and go through the process. The first thing I'm going to do is give the event a name, in this case payload, select the event type, which is an ephemeris event, which means we're going to use an externally generated ephemeris file. So I'm going to click on the ephemeris file selector, and we can drill down and grab that payload ephemeris that we saw earlier. So this tells us what the time span is of that ephemeris file. This is in 2019, which does not correspond to the catalog against which we want to play this ephemeris. So what we want to do is change the time frame of this, and we're going to do it by slipping the time. So that means we're going to change the dates in this ephemeris file from 2019 to 2018. And so we're going to keep this April 8th, 2018 date, and we're going to set the time the same as the time in the original data file, or the original ephemeris file. Now that we have the ephemeris in SEG, do we want to have that ephemeris correspond to an actual object in the catalog, or do we want to create a new object? And for most launches, you're going to be creating a new object. You're going to be sending a new object into space, so we're going to define this as a new simulated object. And we're going to give that new object a name, and then give it a tracking number. And the tracking number of 90,000 in the space surveillance network, any value with the 90,000 or greater is considered an uncorrelated track, or UCT. And that's used to identify objects that are coming into the catalog that have not previously been detected. And we provide some other information about the object, the mass, the drag coefficient, SRP information, and that's used to do force modeling for this object. And that is how we bring an ephemeris into SEG via the ephemeris event. Now what we're going to do is we would generate output for this. Well, of course, this has already been done too for the communication satellite, the second stage and the third stage, as we saw. The other thing is that we want to play these ephemeris files against the catalog that we have. So we needed to create a catalog event. And this catalog event, we can see it's already populated with a number of geostationary objects in the geo orbit. Just wanted to show how we could add more objects, or how we go about creating that in the first place. We have a series of filters, so you can select on an orbit type, or you can type in a space object name, and that will give you a list of objects related to that name. And you can select from this list of objects and then add those into your catalog event. Again, you can sort by or sort by the orbit type. You can sort by country and age and other things. So now that we have that catalog event, and we have our ephemeris events, we have generated the output already, and we can see what the results are by looking at the visualization. And what we want to do is see where this payload object is as it's coming out of the launch. So we can see the orbit tracks showing up, and what we're looking at here is a CZML view, or cesium view. And this shows us the ephemeris that SEG has produced by taking those ephemeris files and sliding them in time, and then taking the states for these catalog objects and propagating these forward over this 2018 time frame. And so we're looking here, we've kind of zoomed in on the payload, and we're watching this payload as it moves forward in time and moves out to the geostationary belt. And at this point, we're seeing the third stage breaking off from the payload. So the payload is being delivered, and the third stage has dropped off, and both of these objects are now at geo orbit. And when this was given to us, there's also a communication satellite that was added, and this payload is going to wind up doing proximity operations around that communication satellite. So we're going to see that happen. But another thing we're noticing here is that the payload and the third stage are basically wandering through this geobelt. So one exercise one might do is take this ephemeris data for these objects and for these geo objects, and run those through a conjunction analysis type of program to see if you can detect if any of these conjunctions might occur, and if there's anything to be concerned about. And here we've seen that the payload has gotten to the communication satellite and is basically cozied up next to it and is in a very close orbit. Again, if we had this data and could feed it into a conjunction analysis tool or a proximity detection tool, hopefully it would alert us that this was going to happen before it was too late. So let's go back and look at the third stage again, because we can do a little bit more with SEG. We don't have to just bring ephemeris events in. We can also modify these events by linking them to do other things. So this is another type of exercise where we say, let's say this third stage isn't exactly what it appears to be. We thought it was a third stage and maybe spent and discarded a geo, but we're going to actually turn this third stage into an actor and have it do proximity operations around another satellite. So I've added another event where I'm taking this third stage object. Again, this came from an external ephemeris that was generated for 2019. We slipped that to our 2018 timeframe and added it to our SEG scenario. And so the description of this is, was the third stage identified correctly? This creates an event that assumes it was misidentified and winds up in circumnavigating an existing communications satellite. And that satellite is, in this example, SkyMuster 2. It's an Australian communications satellite. And we define some of the parameters relative to a natural motion circumnavigation. And what we're going to do when we add this to our scenario and then visualize it, we're going to see that this third stage winds up going into a relative motion around that other communications satellite. And again, this can be useful in generating data to feed into software that is designed to detect when these type of situations might occur, so that if you were operating SkyMuster 2, you would be able to avoid this type of situation or take appropriate evasive action. And so here we see that, in fact, the third stage is wound up next to SkyMuster 2 in a relative orbit. So we might want to look at this data outside of SEG. So in order to do that, we want to go and look at our output data and download some information. So again, SEG produces ephemeris and observations mainly. It also generates data about each object in the scenario. So what we're looking at here, this is for the communications satellite. This is a report that's generated by SEG. And it basically had state information and force modeling information. These are the measurements generated for this communications satellite. Again, the name is ComSat. What we're seeing here is that ComSat has a tracking ID that we gave it. It has an identifier that SEG uses to identify this object in SEG. And for each set of tracking data, there's a tracker number and a set of data in a B3 observations format. And we can download this information to use externally. So we can also download ephemeris data, and we actually want to look at this ephemeris data in an external tool. And the easiest way to visualize this outside of SEG is by downloading a VDF. A VDF is a visual data file, and when we download this, we can open that in our systems toolkit, and we can see the same type of data, but we're going to see it in a different frame than we were seeing it in that cesium view that is native in SEG. So again, before we look at that, we just want to go back and look at the SkyMuster 2 proximity operations. So SkyMuster 2 is 41794. That's the identifier for that object. So when we go back and look at this VDF, this is the data from SEG loaded into SDK. And if we zoom in on this, we're going to see that this is the geosatellite 41794. That's the SkyMuster satellite. And we're going to see our third stage right next to it. And what I'm showing here, I've modified the orbit of the third stage to be relative to SkyMuster 2. And so what you'll see is that the third stage is actually doing an ellipse around the other satellite. And this is what a natural motion circumnavigation proximity operations event looks like when generated by SEG. And so STK really provides us a nice visualization of that. Our next example shows how we can use SEG to achieve two goals. First, we create a realistic training scenario for an operator maintaining a satellite or a satellite catalog, and we'll show how SEG can support a proof of concept study by answering the question, how much tracking data do I really need? So we're going to use SEG to generate ephemeris and observations for a satellite and export that data so it can be used in an external tool to do orbit determination using our ODTK product, which is our orbit determination toolkit. So we're going to start by using a catalog event that's going to contain an object, and we're going to start off with this Jim's demo scenario, which spans 1 day of data. I'm going to open this scenario, and we're going to see in here is that there's a catalog event, and we're going to see that this catalog event contains a single object. Of course, this could be expanded to contain dozens or hundreds of objects, if you wish, but for this example, we're just going to keep it simple and use one single object, because we really want to look at sensor cadence. So what we're doing here is we're defining a cadence for a radar that's, we want to generate 90 tracks per day optimally. Of course, we don't expect to actually get 90 tracks per day based on the trackers that we have, and this is a LEO orbit. So what we're really telling SEG is we want to get as many tracks as we can possibly get. But we're also defining the number of observations per track, which we want to try to keep as realistic as possible. So once we generate the output and we look at these outputs, we can look at the measurements for this satellite that SEG has generated. And we see that we've actually created 25 tracks. And that was the maximum number that we could get. And these tracks, the measurements are being output in a B3 OBS format. And we can download this information for use in our external product. And we also can download the ephemeris, and that can also be used, especially when interfacing with ODTK. It's nice to be able to use the ephemeris to generate data. So the OBS and the ephemeris are both going just in my downloads directory, so I can know where to find those. Now we're going to bring up ODTK, our Orbit Determination Toolkit. Again, this isn't a tutorial on orbit determination toolkit, but so I'm going to go over this very briefly. But basically, we have a scenario that's I gave it the same name as my SEG scenario. And I'm going to create a filter, a satellite, and download the trackers that SEG is using. And these trackers are actually coming from the database that SEG uses. So they're compatible. So when I create the satellite, I'm going to give it a name. And this number, 41356, actually is the SSN number. And that is the tracking data that's going to show up in the measurement files, this 41356. So it's important to link that information in ODTK so I know how to identify the measurements that are coming from SEG, and I'm able to process those. And this initial state and the initial force model information, I pulled this in by looking at the report coming out of SEG, so I know what data to add to create my initial state for my satellite. And what Orbit Determination Toolkit is going to do is we're going to run a filter which is going to take that initial state and propagate it forward and process the measurements coming from these trackers. And here's an example. The one from Puerto Rico has a tracking ID of 831. If we go back to SEG and we're looking at what SEG is producing, we'll see that this tracker number for this first track happens to also be 831. That 831 shows up in the B3 observation file. And again, that tags this range, azimuth, and elevation data, which is also on that line, corresponds to coming from a tracker in Puerto Rico, creating range, azimuth, and elevation measurements for this specific satellite. And we pull those observations into ODTK. At the scenario level, we define the measurement files. And these are the 25 measurement files or observation files that were produced by SEG. And these were we downloaded these from SEG into my downloads directory, and we're loading those into ODTK. And what a filter does is take the initial state for our satellite and propagate that forward and determine what those measurements, at each of those measurement times, what is the actual geometry that it believes, and compare that to the observations that we fed in and adjust the orbit correspondingly. And what we're also doing here when the filter runs is we're generating a predicted ephemeris data. We're going to do 2 days of data. And we're going to do that as part of our study to see how much data do I need to process to get a good orbit estimate in my future. And so the filter is going to generate measurement residuals. And what we expect to see here, we're looking at residual ratios. So this is each measurement residual divided by its white noise. We expect to see a Gaussian distribution, so that should be within a plus and minus 3 sigma range. And the other thing we're noticing here is there's a lot of data. We're having 25 tracks. Each one of these lines really represents a track of data. And from my experience looking at real data, that is a lot of data. That's a pretty good rich environment. So we expect to get a pretty good orbit solution from that. And of course, what we're going to do, each one of these tracks, if you're running an operation, they cost money. So part of our study is going to be how many do we really need? If we had half that many, would we still have a good enough orbit prediction going out for 2 days, say, to satisfy our mission requirements? So what we're going to do is go back to SEG and create another scenario. I could just modify this one and rerun it, but instead I created a second one, my demo 2. And this one is going to have that same object in it. And you can see this, see the orbit here in our CZML view. So it's the same satellite, but what I've really done is change our sensor cadence. So now I'm requesting 10 tracks per day. And again, 10 obs per track at a time step of 6 seconds. And as I said before, we're only doing this for one satellite, but we could obviously add many, many more satellites and have our operator have the task of trying to do orbit determination for dozens and dozens of satellites. So now when we look at the measurements for our satellite, we see that we really do only have 10 tracks, and which is what we expected to get. So we're going to download that data like we did before, and I've created a second ODTK scenario for this demo 2. When we load these 10 tracks in, that's what it looks like. We create a filter for this guy, and we're going to run it. And it's going to process these 10 tracks of data and, again, do an orbit prediction. It's doing a 2-a-day orbit predict when it finishes the filter. And when we look at these residuals, we see that now we have fewer tracks of data, which we expected to see. And we also see we kind of have a big gap here in the afternoon. And we'll see what kind of effect that has. One thing that we requested, again, we just saw that when the filter runs, it's going to generate ephemeris predicts, and it's going to write that data to disk. And what we want to do is be able to see where that data lives. So if I scroll down here and click on the output directory, it's going to tell me what directory those files exist in. So we see it lives in that ephemeris directory. So I open that up and I see that, so I've renamed the .e file. So there's one for the sparse tracking that we just did. There was one for the dense tracking, which was the one with 25 tracks per day. So now I'm looking in STK, our systems toolkit. And I've created an object for the dense and the sparse tracking. And I've pulled those ephemeris files in. And when ODTK produces an ephemeris file, it provides a covariance ellipsoid, or covariance data that we can visualize in SDK. What we're seeing here on the left, lower left, that's the truth ephemeris coming out of SEG. So that's the 41356 satellite. The next one over was the sparse, or was the dense tracking object, and then the third one was the sparse tracking object. And you can see as we move forward in time, these covariance ellipsoids are changing based on the tracking data that's being processed. And when we start tracking data, these covariance ellipsoids collapse, and in the absence of tracking data, they start to expand as we propagate forward without any information. So the more information you have, the smaller you expect these ellipsoids to be, and the more information you have, the closer you expect the two satellite objects to be in SEG. So again, there's the truth and the dense tracking, and the sparse tracking is a little ways away. And again, we're looking at, this covariance is growing for the sparse tracked object during that period where we don't have any tracking. But if we animate to where we pick up that final tracking at the end of the day, we see that the blue ellipsoid has collapsed again. And so and without any more measurement data, both of these ellipsoids are growing. But are they growing significantly different enough to justify spending the extra money on getting those extra 15 tracks of data per day? So based on your mission requirement, you might think, well, I can get away with 10 tracks, maybe I can get away with even 5 tracks. It really depends on what I want to do. So as a data flow, what we've done here is we generated measurements in SEG. This is our SEG interface. We downloaded that data and processed it in ODTK, our Orbit Determination Toolkit, and we use this to export ephemeris that also contains this covariance ellipsoid information.
All right, so as Patton said, you fight like you train, which means you should train like you're going to fight. And to do that, you need a tool that will generate data that's as realistic as possible. And that is our goal with SEG in order to support test, training, tactics, and exercise missions. So thank you for listening. And I think we might have some more questions.
If there are other sensors besides the known SSN, can these be added?
Yes, there are services that we have that allow you to enter sensors.
Awesome. And another question, how can I get the data such as numbers and graphs from SEG?
You can download, I think, everything. Depends on what data and graphs you're looking for. But yeah, you can download the PDF, you can download measurements. We have reports that are basically Astrogator summary type reports. And those you can either copy to a clipboard or download those.
Great. And then is SEG an SDK module of its own, or is it its own environment?
So SEG is its own product, its own environment. SEG is runs through services and uses a backend database as data storage. Whereas SDK is a desktop application and uses a file system, uses files as its storage medium. However, data can be downloaded from SEG to be loaded into SDK. And obviously, you can take ephemeris out of SDK and load that directly into SEG as well.
Great. And what observation formats are supported?
We support the B3 observation format.
Great.
Which is discussed in further detail in our ODTK documentation, and I don't know if that's also in our SEG help online as well.
Definitely. And then what measurement types are available?
We support radar, which is azimuth, elevation, range, and Doppler. We support right ascension and declination, both ground-based and space-based.
Great. Thank you guys so much. Thank you, Jim, for presenting, and thanks, Ben, for helping out with the question. And thank you all for joining the webinar. For those questions that we didn't get to, we will be answering those individually after we sign off. Make sure to sign up for our next webinar on January 31st on scheduling for space system operations. And just so you guys are all aware, you will be getting this presentation sent in an email to you in the near future. So stay tuned for that. And thank you again. We'll see you next time.